Okay, at the end of the last video, we talked briefly about Epsilon-nought. Now, Epsilon-nought is part of an entire family of epsilons, which we will be dealing with in this video. Epsilon-nought, as we stated before, is defined as an infinite tower of omegas. And it too has a fundamental sequence, and we would normally think of the fundamental sequence intuitively as omega, omega to the omega, omega to the omega, O to the omega. But for technical reasons that we'll go into a little bit later, this fundamental sequence actually starts at 1 and then continues on in the omega fashion. So it starts at 1, and then it's omega, omega to the omega, blah, blah, blah. So this is a slight difference that doesn't really matter too much, but it's important for us to know so that when we diagonalize, we pick the right one type of thing. So this is the fundamental sequence for Epsilon-nought. Now, Epsilon-nought is an interesting ordinal because it's our first fixed point. And what a fixed point is basically, in this case, it satisfies the equation omega to the A is equal to A. And what I mean by this is if I take omega to the Epsilon-nought, it just equals Epsilon-nought. And we can kind of see this. What happens if we take omega and just add an infinite stack of omegas on top of it? Well, this is still just going to be an infinite stack of omegas, which is the exact same thing as here. And it's just going to equal what we started with, which is Epsilon-nought. So we've kind of reached a little bit of a problem here, because how do we get past this? How do we, if we can't get anything bigger by taking omega to the power of this, how do we make bigger ordinals? And the answer is simply by adding 1. No matter how big an ordinal is, we can always add 1 to it and get a bigger output. So if you think of plugging in f to the epsilon-nought of 3, what kind of number do we get? Well, when we diagonalize, we take the third element, which in this case, it's not omega to the omega to the omega, which is what you would think. It's actually omega to the omega, so just keep that in mind. And f to the omega is something that we went through before. This turns into that omega squared times 2 plus omega squared, omega times 2 plus 3. So we break this apart and it ends up something like this. And this is something that we did in the past example. So already we have an idea of the kind of numbers that epsilon-nought can make. But what happens when you plug in epsilon-nought plus 1? Epsilon-nought plus 1 of 3. Well, now we have a successor that we can recurse. So we have 3 copies of the epsilon-nought function of 3. So we have this, which is going to be a huge number, and we end up plugging this huge number into here, which means that we're going to have a tower of omegas that's this high. So it seems that we've successfully gotten past the fixed point trap. And that's what this is called. When you add 1 to something to get past a certain point, when it reaches a point when it can't get past, it's called getting past the fixed point trap. So we are going to be doing that a lot. So now what we want to do is we want to take this idea of adding 1 to epsilon-nought and create a new fundamental sequence. Well, what happens if we take our omega to the epsilon-nought, which we know is simply just epsilon-nought, and we add 1 to this? Well, instead of just collapsing on itself like it does here, this starts to break apart. So let's say that this is diagonalized to 3. I'm not sure if I mentioned this, but when I do the square brackets like this, that means I'm diagonalizing. I just don't want to put this into the fast-growing hierarchy every time and just make it messy. So this is another way of denoting a diagonalization. So let's say I have this diagonalized to 3. Well, the first thing we want to do is we want to use rules of exponents and turn this plus 1 into omega to the epsilon-nought times omega. So let's do that. Omega to the epsilon-nought times omega. Well, now this is all by itself now. So this is going to collapse in on itself because of this rule right here. So we're just going to have epsilon-nought times omega. Oops, and this is diagonalized to 3. So now this is going to turn into a 3 here because we have a lone omega. So it's going to equal epsilon-naught times 3. We can break this apart into epsilon-naught times 2 plus epsilon-naught. This turns into omega to the power of omega. Epsilon-naught times 2 plus omega to the power of omega. So we can already see that this is starting to break apart into something much, much larger than epsilon-naught. And this is exactly what we want. We don't want to just put omega to the power of this or whatever and have it just turn into the exact same thing we started with. We want something bigger. So this is starting to expand into something much, much larger. So now, if we pick this as our starting point in the fundamental sequence, we can create a new fundamental sequence. So we have, let's say we have omega to the epsilon-naught plus 1. And let's go on to omega to the omega to the epsilon-naught plus 1. Omega to the omega to the omega to the epsilon-naught plus 1. So this kind of has the same form as the fundamental sequence for epsilon-naught in that it's a tower of increasing omegas, but it just has this little element on top that's going to get us out of that fixed point trap so we can get to bigger ordinals. And another reason for this, this format of fundamental sequence is that it has the elegant property that the limit of this, an infinite tower of omegas with just epsilon-naught plus 1 on the top, whatever that means, is equivalent to an infinite tower of epsilon-naughts. And I'll show you quickly why this is the case. Let's just take a random one. Let's just take omega to the omega to the omega to the epsilon-naught plus 1 and just do some rules of exponents on it. So first thing, we'll turn this plus 1 into a times omega on this line here. So this is equal to omega to the omega to the epsilon-naught times omega. This collapses because it's all by itself now. So it's going to equal omega to the epsilon-naught times omega. And now we're going to use rule of exponents to turn this here into omega to the epsilon-naught in brackets, and then have this outside of the brackets. That's one of the rules of exponents. Now we're going to do something a little bit tricky, and I'll explain why this works. Omega to the epsilon-naught 1 plus omega. Okay, so this kind of came out of nowhere, but the reason I can do this, if you remember, is because 1 plus omega is different than omega plus 1. 1 plus omega is still equal to just omega. So I'm allowed to replace omega by 1 plus omega, and arithmetically that's perfectly valid. And another thing that we can do in this step is just replace this by just epsilon-naught, because once again, this is by itself, so it just collapses. So let's go omega to the epsilon-naught 1 plus omega. So now let's multiply this out. We have epsilon-naught to the power of 1 plus omega. So we're going to turn this into a times epsilon-naught to the omega. So this turns into omega to the epsilon-naught times epsilon-naught to the omega. And this is another opportunity to do the operation that we did here. We turn this multiplication, we put it in brackets, and then put this on the outside. So this turns into omega times epsilon-naught to the epsilon-naught of omega. This collapses, and we end up with just epsilon-naught to the epsilon-naught to the omega. And if your starting point is 4 omegas with this on top, you'll end up with 3 epsilon-naughts with an omega. And you can see the trend. The limit of this, an infinite tower of omegas, is going to equal an infinite tower of epsilon-naughts. So this has a fairly elegant solution in that you can write it in this way here. And the way we denote this, the limit of this, is with epsilon-one. So epsilon-one has that fundamental sequence, omega epsilon-naught plus 1, omega to the epsilon-naught plus 1, etc., 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 etc. And the way we would break that apart in the fast-growing hierarchy, I wrote it down preemptively just because these things take a little bit of time to work out. So we'll just go through it a little bit. So epsilon-1 of 3, we take the third element of epsilon-1, which would be omega to the omega, epsilon-naught plus 1. We take this and plug that into the fast-growing hierarchy. And then we just break it apart. We do rules of exponents and diagonalization, and we keep on, this turns into Epsilon-nought times 3. We break off 2 epsilons, leave it here, and this is a third Epsilon-nought, which turns into omega to the power of omega, which breaks apart into this thing here that we've seen before. More rules of exponents to bring this 3, or to bring these addition terms down into multiplication, and then it breaks apart further and further and further and further and further. And we keep on doing this until we finally get to a successor that we can plug into the fast-growing hierarchy, and we can recurse this function. So this turns into something that's much, much, much bigger than Epsilon-nought or whatever. So we can use this definition of escaping fixed point traps and creating new fundamental sequences to keep this trend going. What if we have a fundamental sequence that starts the same, but now we have Epsilon-nought plus 1. And I want to mention really quick, if this isn't entirely clear, Epsilon-one also satisfies this equation here. Omega to the a is equal to a, because omega to the epsilon 1 or whatever, it has the same properties as this. Adding another omega to this infinite tower of omegas is not going to change the number at all. So this is just equal to Epsilon-one. So the same way, we have to add a 1 to this in order to get further. So once again, we're escaping the fixed point trap, and we're creating a fundamental sequence that goes like this, whatever. Plus 1, omega to the omega to the omega, Epsilon-one plus 1, blah, 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 blah. And we're going to call this Epsilon-two. And it's arithmetically equivalent to Epsilon-one to the power of Epsilon-one to the power of Epsilon-one, blah, 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 blah. And if you were to plug this into the fast-growing hierarchy, you do the exact same thing, except you start with the third element of the fundamental sequence, and then you go from there. And this keeps going like this. We can do Epsilon-3, which is infinite tower of omegas with Epsilon-two plus 1 at the top, Epsilon-4, Epsilon-5, and we can even put infinite ordinals in the subscript of the epsilon. So we can have epsilon sub omega. And this would have the fundamental sequence of Epsilon-one, Epsilon-two, Epsilon-3, blah, 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 blah. And plugging this into the fast-growing hierarchy, F sub omega, sub epsilon of 3. Take the third element of this, and we end up with F sub epsilon sub 3. And then we go from there. So any infinite ordinal that we've previously constructed, we can put in the subscript of the epsilon. We can even put another epsilon in here. So we can do epsilon, Epsilon-nought, which would diagonalize as epsilon sub omega to the omega, which would be epsilon sub omega squared times 2. So when we have these infinite ordinals in the subscript, we treat them exactly the same as we did before. So we use the same rules to deconstruct these as we did before. And it pretty much keeps on going from here, whatever. We can have epsilon, epsilon, Epsilon-nought, epsilon, 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 Epsilon-nought. And we can even have an infinite nesting of epsilons, which would have the fundamental sequence of Epsilon-nought, epsilon, Epsilon-nought, epsilon, epsilon, Epsilon-nought, blah, 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 off into infinity. And this is something called zeta-naught, which we'll go into in the next video.